In this video, I'll demonstrate how to use MATLAB to perform the matrix operations I talked about in the previous video. I'll start by talking about how to use MATLAB's matrix operators to perform matrix addition, subtraction, multiplication, and transposition. Then I'll explain how to implement these types of operations using looping structures, because programming the operations ourselves will help us understand these processes. MATLAB has operators that are dotted, they're preceded by a period, and undotted. The undotted operators perform matrix operations. To add and subtract matrices, use the plus and minus signs. Addition and subtraction are the same process for array and matrix operations, so we have only one set of addition and subtraction operators. Multiplication of matrices according to the rules of linear algebra is done with the asterisk symbol. In matrix multiplication, the inner matrix dimensions must match, unless one of the operands is a scalar. In multiplication between a scalar and a matrix, each element of the matrix is multiplied by the scalar. Exponentiation is done with a caret symbol. This operation multiplies a matrix times itself the number of times specified by the exponent. So the result of a cubed results in a being multiplied by itself 3 times. To transpose matrices, you can use either a single quote or a single quote with a dot in front of it. Dot quote transposes the elements of an array. Quote with no dot also transposes the elements of the array, but it also takes the complex conjugate of the array. That changes the sign of any imaginary parts of the numbers. Now let's do a few examples of these operators. First, I'll set up a couple of arrays to work with. A equals 1, 2, 3, semicolon, 4, 5, 6. And B equals 0, 2, 1, semicolon, 4, 0, 3. I can add these two arrays by typing A plus B, and I can subtract B from A by typing A minus B. Matrix addition and subtraction require the matrices to be the same size, and these arrays meet this requirement. I can't multiply A times B, though. The inner dimensions don't match. A has 3 columns and B has only 2 rows. However, if I create another array, C equals -2, 1, semicolon, 0, 3, we can multiply C times A, since the number of columns in C is 2, which matches the number of rows in A. And we can multiply A times the transpose of B, since the transpose of B has 3 rows. The matrix exponentiation operator can be used to square the matrix C. The result is the multiplication of C with itself. Since the number of columns in the first matrix has to match the number of rows in the second, to multiply a matrix by itself, it must be square. Finally, I'll transpose a matrix D which has complex values. I'll set D equals 1 plus J, J, 1 minus J, semicolon, 2, 3, and 1 plus 2 times J. If I transpose D with the dotted operator, so D dot, quote, the rows convert to columns and vice versa. If I take its transpose using the undotted operator, however, the imaginary components of the complex coefficients change sign. One of the most common errors I get when working with matrices occurs when the dimensions of my arrays don't conform to the rules of linear algebra. So it's helpful to be able to determine the sizes of your arrays. MATLAB provides several commands to tell you how big your arrays are. Length returns the number of elements in the largest dimension of an array. This is particularly useful for one-dimensional arrays, where length returns the number of elements in the array. Size returns the number of rows and columns in that order in an array. If you want to know the total number of elements in an array, the numl command returns that. Now that I've covered the built-in matrix operators in MATLAB, I'm going to describe how to implement matrix operations with looping structures, rather than MATLAB's built-in operators. This is important for 2 reasons. First, it provides good practice in using looping structures. Second, programming the matrix operations helps you understand how these operations work, which will help you catch errors if you make them when you're using MATLAB's built-in operators. The first and probably the simplest operation to program is matrix addition. In matrix addition, the element of the resulting matrix is just the sum of the corresponding elements of the operand matrices. So if I add matrices A and B to get C, the element in the jth row and the kth column of C is the sum of the elements of A and B in the jth row and kth column. Since we need to add the corresponding elements in these matrices for every possible combination of rows and columns, we can use two nested for loops. The order in which we loop through these elements is optional. We can make the outer loop select the columns and the inner loop select the rows without affecting the results. Finally, we need to determine what M and N are. M is the number of rows in the matrices, J corresponds to the rows, and N is the number of columns, so we can use the size command to determine the size of the matrix and return the number of elements in those dimensions. I've used the A matrix to decide the number of rows and columns. Next, I'll program an inner product between two vectors. To perform an inner product, I multiply a row vector, A, times a column vector, B, to get a scalar, C. The inner product is the sum of the products of the individual elements in the A and B vectors, which requires that the A and B vectors have the same number of elements. So, the main part of the code will be a for loop that multiplies corresponding elements in the A and B vectors. As we multiply these elements, we also need to keep a cumulative sum, so that when the loop's done, we will have performed the appropriate multiplication and summation processes. Since the value of C is on the right-hand side of the assignment operator, it needs to be initialized to 0 before we enter this loop. Finally, we need to determine how many elements are in the A and B vectors. I've arbitrarily based my number of elements on the A vector and assumed that the B vector will have the same number of elements. Now I'll look at multiplying two matrices using looping structures. Multiplication of matrices involves creating an inner product for every combination of rows and columns of the matrix. The important part of this process is to perform the inner product between the appropriate rows of A and the columns of B. So the element in row J and column K of C is the sum of the products of the jth row of A and the kth column of B. The index I is used here to loop through the elements in these rows and columns. In order to do this process, the number of columns in A has to be the same as the number of rows in B. Since I'm performing a cumulative sum of these elements, I need to initialize the element of C at the jth row and kth column to 0. Now I have to perform this inner product for every combination of the rows in matrix A and the columns in matrix B. So A has M rows and B has P columns. Since this is our most complicated case so far, I'll demonstrate its implementation in MATLAB. I'll start by creating a script file and then convert it to a function, since I usually feel like it's easier to debug a script file than a function. I'll name my file matrix_mult, and it'll be in the working directory. The first thing I need to do is set up a couple of arrays to multiply. I'll create a matrix A that's 1, 2, semicolon, 3, 4, semicolon, 4, 5, and a matrix B that's 1, 2, semicolon, 3, 4. My looping structures will depend on the sizes of the arrays I'm multiplying, since in the final version of the code I won't know beforehand what the sizes of the arrays are. I'll have my program determine that with the size command. The size command returns two numbers, the number of rows and the number of columns in the argument matrix. I can set this up to return these values with separate variable names if I want. To do this, I can set nrow A, comma, ncol A equals size of A, so that nrow A and ncol A provide the number of rows and columns in A. I'll also set nrow B, comma, ncol B equals size of B, so that n row B and n col B contain the number of rows and columns in B. To keep things simple at first, I'll just calculate the inner product of row 1 of matrix A and column 1 of matrix B. I'll use the variable j to represent the row of matrix A and k to represent the column of B. The result of the inner product will be in the variable c, so I'll initialize c equal to 0. Now I'll loop through the product of the elements in the columns of A and the rows of B. I'm going to use a variable I to address these terms, so my for loop will be for I equals 1 to n col A. I could use n row B instead of n col A, since those have to be the same for any valid matrix multiplication. In the loop, C is the accumulation of the products of A of j comma I and B of I comma k. So C equals C plus A of j comma I times B of I comma k. That's all I need to do for an inner product, so I can end this for loop. I won't follow this command with a semicolon because I want to see the results to make sure it's correct. Now I'll save the file and run it. The first time through the loop, I multiply 1 times 1 and add it to 0, so c equals 1. The second time through the loop, I multiply 2 times 3 and add that to 1, which gives c equals 7. Since that looks right, now I can add my loops to go through all the rows of A and all the columns of B. I also need to make C a matrix whose rows are J and columns are K. I'll also add semicolons to the calculations, since I don't really want to watch them scroll past. To test the file, I'll save it and run it. This element of C is 28, which is equal to 4 times 2 plus 5 times 4, so it looks like my program's working. Finally, I'll add some error checking to make sure that the number of columns of A is the same as the number of rows of B. If this is true, I'll do the multiplication. But if it's false, I'll set C equal to not a number and display an error message. Finally, I'll add a function declaration statement and eliminate the definition of A and B in the function and save the file. For my final checkout of the function, I'll define A and B in the workspace and call the function. I'll check that against MATLAB's built-in matrix multiplier. Looks like it's working. To test the error checking, I'll try multiplying A times itself. Since the inner dimensions don't match, it should give an error message, which it does. Now that we've gotten a little more insight into the basic matrix operations, we can talk about matrix inversion in the next video. This will lead us to an extremely useful application of linear algebra, solving systems of linear equations.